Identifying and understanding probability density functions, part 2. This will make sense if you watched part 1. Part 1 finished with us completing part of this task here for the given rule. We sketched the graph. It's a piecewise type scenario, and we showed that it is a probability density function because the integral between negative infinity and infinity with the help of our limits came out as 1, and that's one of the conditions. So that basically means that yes, it's a probability distribution function because both of the conditions are satisfied. So let's do part C now. Part C, find the probability that x is greater than 1 where the random variable x has a probability density function, so it's given. Okay, and then we're going to do the same thing with graphics calculator. So the probability we require is when the limit as k approaches infinity for the integral. Now, the k goes up here like last time. This is x greater than 1 here, so the lower terminal will be 1. And we have 2e to the negative 2x dx, our function given. Now, reason why, because there's two parts to this piecewise function, the reason why it's this particular function you see there, we'll just look at the aspect, the interval of x we're dealing with. It's above 1, so that's where that rule 2e to negative 2x is apparent. Okay, so let's do that integration, and it's the limit as k approaches infinity. Take the integral, so we have negative e to the negative 2x between 1 and k. And we're writing that out now in full with the limits subbed in, with the terminal subbed in. And we have, so it doesn't look like an x there, just to be sure. And we have that there. Now, just explicitly, the contents of the square brackets are written there, and you can see we have 1 over e squared, and we have negative 1 over e to the 2k, and as k approaches infinity, we have 2 times infinity, or 2 times very big number, so it's e to a very big number, which is very big, and the negative 1 over a very big number approaches 0 from the negative side. So that's 0 plus 1 on e squared. As a decimal approximation, 0.1353 if we take it to 4 decimal places. Let's see if we can get that answer now, verifying with the graphics calculator. So part D, verification with the graphics calculator. Okay, so we've got our TI Nspire in this particular case, got calculus, and let's try numerical integral, and we've got 2 times e to the negative 2x, and with regards to x. Now the limits here, let's think about it. We can't put infinity on, I'm using a non-CAS calculator, I can't put infinity there, so I'm going to put something pretty darn big like 10 to the power 9, I am told works quite well. And to test that it is a full distribution, this should be 1, because remember, knowing the nature of this function, anything less than 0 is, if the graph of that sits on the x-axis, there's no area under that, is there? There's no value. So we could go from 0 to 10 to the power 9, okay? And that should come up as 1, because 10 to the power 9 is extremely big. Oh, good, it does. So if we use that again, but we change the limit to the 1 because we want from 1 upwards, do we get 0.1353? We do. That's good. So that's verified with graphics calculator. Okay, it's an extremely good approximation, even if we can't use infinity to 4 decimal places. That's no sweat at all. Okay, so there's a calculator approach. Last part of the video, second example, given that the following functions are probability density functions, so that's a given. So those attributes and those conditions that we were checking for in the previous example are given now. Okay, so we're going to apply that. We have to determine the value of parameter A in each case for these two functions here. So part A first, we have a function that's defined as some real number A times x to x minus 1 to the power 2. That's between 0 and 4 inclusive. Elsewhere, it's just 0. When we get to part B, it's a e to the negative 4x when x is greater than 0 and 0 elsewhere. Okay, so that's the expression. It's got to be equal to 1 because we're told that it's a probability density function. So we can put the constant out the front if we wish. And we do wish. Using some method of integration, whether substitution or integration by recognition, which we've done in the past, that would be, or numerical type of integration, perhaps if you could do that. We've got that there between 4 and 0, and we've got a out the front there. That integration step will depend on what subject you're studying and applying this to. If you don't have integration by substitution, we've done integration by recognition, or there's other options there. Alright, so we're looking at putting in the terminal values, sub them in. So we have 4 minus 1 cubed over 3 minus negative 1 cubed, because 0 minus 1, negative 1 cubed over 3, that equals 1. So 3 cubed is 27 over 3 is 9, and negative 1 cubed is negative 1, so that's negative a third, so that's plus a third, because it's minus negative a third. Okay, add those two together and divide through, and you get a is 3 over 28. So just remember the second part we had to determine a for this expression here, for this piecewise function, and a e to the negative 4x when x is greater than 0. So we've got that according to the function, which means we've got this it's a e to the negative 4x dx, I think, if I remember correctly. That equals 1. Yes, it was. Okay. Moving down. Too much. Alright, so next. Okay, constant a is out the front now. So it equals a times the limit as k approaches infinity from 0 through to k of e to the negative 4x dx. That equals 1. Alright, subbing those values in, we have a times the limit as k approaches infinity so we have e to the negative 4k minus e to the power 0, which would be 1. That equals 1. And let's look at what happens there. Now, e to the negative 4k is the same as 1 over e to the 4k. And as we have k approaching infinity, that means we have 4 times k will become very, very, very large. Okay, so that would be e to a large number, which means 1 over a large number, which tends to 0. So we have 0 minus e to the e to the 0, which is -1. So a times -1 is 1. Except for I didn't integrate properly. Using that rule there, e to the integral of e to the ax dx is 1 on a times e to the ax, where a is a constant. I forgot to factor that constant in, so I've just made an adjustment there. So it's -1/4 e to the -4x minus -1/4 e to the 0. Sorry, I've got to put my k here. That'll be a k. Okay. All right, so means we have -1/4 there. We have -1/4 there. But really it's the same deal, because e to the 4k as k approaches infinity is e to the infinity, which is very big. 4 times very big is still very large, and you still tend towards 0. So that bit's the same. So that second term there, once we sub in 0, we for the power, we got minus -1/4, which is +1/4 e times 1. So that's +1/4. And this term on the left, as we said, is tends to 0. So 1/4 a equals 1. A is 4. And despite a couple of little errors, it's all good.